No, I couldn't even pay attention to that. Yeah, we'll just look at. Okay. Yes. Okay. And because if not, then I want to. It's entirely possible that a couple people might sneak in after they
Or is
start.
it curl just because
Ready? Okay. You guys All right, thank you very much for coming this morning. I do promise that this presentation will be a nice way to start your week. This is a spectacular group of kids that I've thoroughly enjoyed, and they've got a couple of really quite entertaining bits in their presentation, so I'll tease you with that. So with no further ado, I introduce you to students from Bishop Carroll in Calgary, Alberta.
We are the Peanut Gallery from Bishop Carroll High School in Calgary. We've been working since November with Tracy and Nicole and Gosha on 2 projects actually, the first of which is airborne peanut allergies and mucus.
So we got into this topic because as we were growing up, we noticed there's a huge crackdown on nuts in the food lunchroom. So no more nuts for us and no more peanuts. And so we noticed that there seemed to be almost like an increase in nut allergies in our society. And there's like this huge kind of almost like nut scare and peanut scare. So we were interested in that. And so we discovered we were particularly interested in the anaphylaxis reaction and claims that there are airborne allergies, which to our understanding, we believe that peanut proteins, which cause the allergy, are denser than air, so we're not really sure how they were able to be aerosolized and actually induce a reaction through inhalation. So we mimicked the inhalation by using hyaluronic acid, which is this mucus-like substance, and we basically tried to see if any proteins would attach to it. And so, as you can see here, this is the population distribution of Canada, and more or less likely, about 350,000 people could have peanut allergies, and of those people, about 318,000 could have moderate to severe allergies, meaning they will need medication to suppress their reaction. And interestingly enough, Eric, one of our members here, he does have a moderate to severe allergy. So, yes.
Okay, so our research was conducted using the technology of X-ray fluorescence on the IDEA's Beamline. That it's using the property of atoms' electrons to gain and lose energy and emit photons as a result. So basically, the light from the synchrotron, which is filtered by the monochromator into just X-rays, is incident upon a sample which gains, like the electrons in this sample gain energy. Others, like they jump shells, others go back to where the first ones were, and they emit photons in wavelengths and energies that are sort of comparable to the binding energies of the electrons in the sample. So basically, the light that's detected by the silicon drift detector with the beryllium window here can tell you the chemical composition of the atoms that are making up your sample. We noticed that in our peanut proteins that we were investigating, one of the major components that we could easily identify using this beamline would be potassium. So we were looking in our samples of mucus for traces of potassium as measured by our beamline.
So as mentioned, our hypothesis in this experiment was that the density of air is so much less than the density in the peanut proteins that it would not be present in our hyaluronic acid samples.
Okay, so as Sydney was saying earlier, we use hyaluronic acid to stimulate the mucus. And what we did is we took 3 different kinds of peanut samples. We had crushed, we had whole, and we had shells.
And so we exposed the hyaluronic acid to the different peanut samples for variable amounts of time and different distances as well. And we also decided to do some real life situations to make it somewhat more applicable. So we did some samples in our school lunchroom, just on a table by itself in the corner. We also did one sample in the lunchroom while all of us gathered around and ate a bunch of peanuts. And then we also did one where we were crushing peanuts right next to the sample to simulate someone chewing maybe next to someone with allergies.
Okay. When we did our scans, we did it in a vacuum because argon, which is naturally found in our air, has the same peak, or not the same, but a very similar peak as potassium. And we didn't want the scans to conflict when we were measuring our data.
And setting up our samples, we decided to use Kapton tape, but then we were also introduced to Mylar tape, which Eric will now tell you about.
So we kind of came across this dilemma of which tape is better, Kapton or Mylar. So what we did was we wrapped the sample with about 7 wraps of tape and then scanned it to see what the results were. And as you can see, basically the same compository elements. There's argon, iron, and nickel here in relatively the same amounts. And the green line right here is just a blank scan that we ran. And the red is the Mylar, and the blue is the Kapton tape. So we've zoomed this in after normalizing it. So these little peaks that you see here, we can just contribute to noise because they're not even noticeable on the original scan.
Got a couple pictures of the sample taking in action right here. As you can see, we've got our glass slides as well as Eric preparing some of the samples. We've got the crushed peanuts there, and we've got some of the work with the tape, which we eventually chose Kapton right here. Alright, so looking at the actual data from our peanut experiment. So this is a graph of the X-ray fluorescence scan of our peanut control sample. So this sample was just straight up peanuts. We've zoomed in on the potassium peak here. So as you can see, we've got a higher photon count for our energy level of potassium. So using this graph, we can kind of assume that there is in fact a detectable level of potassium within our sample that was just peanuts. Now as you'll see on the next graph coming up right here, here's the peanut lunch scan. This is the full spectrum. So this is, for a bit of context, you've got a cafeteria table, you've got about 10 kids, you've got a kilogram of peanuts, everyone is eating them and throwing them around. So we figured if a scan was going to have peanuts in it, it was going to be this one. So we see we've got a couple elements here. We've got calcium, bromine, iron, nickel. All the other peaks are mostly either noise or secondary peaks of elements that are already labeled. And if you look to the right of calcium, sorry, to the left of calcium rather, right here, this tiny little bump is potassium. So for our purposes, that's considered noise, which is illustrated also on the next slide, right here. So this is a normalized graph, which is normalized to the current of the beamline, and each graph is normalized to each other, so it's acceptable to compare them. As you can see, we've got our peanut control sample in blue, the pure peanut sample. This is once again zoomed into our potassium peak, so there's a definitive potassium peak there, but if you look at our green hyaluronic acid sample, so blank control scan, as well as our orange peanut lunch sample, nearly identical when we're looking at the potassium peak. So using this, we were able to conclude that there were no traces of peanut proteins within the sample that we judged most likely to contain them.
So the very first thing that we scanned was the peanuts, then our hyaluronic acid sample, and then we used our most likely sample, which was the peanut lunch sample. And we found that our results did support our hypothesis, but then we realized we didn't have much else to do. So we thought, what were some sources of error that we could look at that might have given us more to look at? So our first source of error was actually miscommunication between us and our scientist mentors. We ended up drawing our hyaluronic acid straight onto glass slides. They intended for us to use cover slips. So when we got to the CLS, we actually had to use forceps to scrape the hyaluronic acid onto cover slips. So that can help to explain a lot of the metals that we saw in our scans. Another source of error could be that there may have been potassium in our sample, but it was just too low of a concentration for us to see it on our Beamline scans. Also, we did stop after our first peanut lunch sample when we didn't see any potassium. So it's unlikely, but there could have been potassium in our other ones. And lastly, our environment at school when we were taking our samples was not perfectly controlled, so there could have been some contamination there.
All right, so conclusions. Our main thing was hashtag no K is okay. So because of the potassium that we didn't find, our hypothesis was actually supported, as you saw on that last graph. The control scan of the hyaluronic acid was nearly identical to the scan of the peanut lunch, which was what we judged to be most likely to contain peanuts. So our data suggests that the actual airborne allergies by inhalations may not be possible. However, I think there's still quite a bit of room for future research, and Eric's going to talk about that.
Yes, so with having a peanut allergy, I know firsthand what some of the stresses are when you see a peanut or you smell a peanut, because you really just get afraid of it, like you're all worried about contaminants you're going to get on your hands. So I would like future research to be into the physiological and psychological effects that someone who sees peanuts and has a peanut allergy, what that has on their body, because I've heard of people who just can't even smell it. And based on our data, that doesn't really match up, so I'd like to do some research, maybe do some placebos to see what's actually going on if someone's just so stressed out that they're self-inflicting a reaction on themselves. Another point to consider is there is an unknown concentration or amount that is required to have a reaction. So if we could find some sort of baseline or range to determine this amount will cause a reaction or not.